Hello dear students, today we are going to discuss geometrical isomerism and nomenclature of geometrical isomers. The main objectives of the topic are to know about the representation of three-dimensional molecules in two dimensions by wedge and dash, Newman and Sawhorse projection formulas. Next is interconversion of wedge and dash, Newman and Sawhorse projection formulas. Next, geometrical isomerism and criteria of a compound to show geometrical isomerism. Next is cis and trans nomenclature of geometrical isomers and assignment of E and Z nomenclature for compounds having 1 and 2 double bonds. Let's start with a brief introduction. Stereoisomers which cannot be interconverted into each other freely, that is, without breaking of bonds, are called configurational isomers. Geometrical and optical isomers are two important types of configurational isomers. In geometrical isomerism, pairs of isomers exist with groups in the molecule held rigidly with respect to one another. Geometrical isomerism is possible due to restricted rotation of the groups about the carbon-carbon, carbon-nitrogen, nitrogen-nitrogen double bond and rings. A disubstituted alkene with one hydrogen at each carbon of the double bond shows geometrical isomerism, which are designated as cis or trans or alternatively E or Z. An alkene with 3 or 4 different substituents attached to the doubly bonded carbon atoms may exist as geometrical isomers designated as E or Z. A sign of E or Z configuration depends upon the mutual relationship between high priority groups as determined by CIP convention on each end of the double bond. Now, coming to the representation of three-dimensional molecules in two-dimensional plane, perspective and projection formulas. Stereochemistry deals with the three-dimensional molecules, so it's essential to deal with three-dimensional molecules on two-dimensional paper or board. Various graphical methods have been developed to visualize three-dimensional representations on two-dimensional papers. First is wedge formula. In this representation, the bonds projecting out of the plane of paper are shown by solid wedge, and the bonds which are projecting down the plane of paper are represented by dashed wedge. The bonds which lie in the plane of the paper are represented by solid line. In case of tetrahedral atom, two bonds are drawn in the plane of the paper with an angle of 109 degree, and a wedge and dashed bond are drawn close to each other. Trigonal planar molecules are drawn either with all bonds in the plane of paper separated by 120 degree angle, or one of the three bonds on plane of paper and one behind and one towards the observer. Now, Sawhorse projection. A Sawhorse projection is obtained by looking the molecule sideways from above or at an angle to the bond joining the two carbon atoms. All bonds are drawn with solid lines. 3 bonds at each carbon atom are drawn in the shape of Y or inverted Y. The 3 groups at one carbon atom can be rotated with respect to another carbon atom. Next is Newman projection. The Newman projection of the molecule is drawn by looking at the molecule directly in front of the carbon-carbon bond. The front carbon is drawn as a point and the back carbon as a circle. Each carbon has 3 bonds radiating from it and are separated by 120 degree angle. Next is Fischer projection. Fischer projection is the simplest method of drawing tetrahedral molecules, especially chiral molecules, on the paper. These projections are particularly useful for carbohydrates, amino acids and other molecules having more than one chiral centers. To draw the Fischer projection, the three-dimensional representation of a molecule or module of the molecule is held such that the vertical bonds from the tetrahedral carbon or stereo center are directed away from the weaver and horizontal bonds are directed towards the weaver. The only atom which lies in the plane is the stereo center itself. The molecule is written as a cross, the tetrahedral carbon being represented by a point at which the bonds cross. The horizontal line represents the bonds towards the weaver and vertical lines represent the bonds away from the weaver. The other rule to remember when drawing the Fischer projection is to draw the carbon chain of the compound vertically with the most oxidized carbon at the top. The various types of representations can be exemplified with the case of plus-minus glyceraldehyde. In testing for superimposability, Fischer projections should be treated differently from the models. They can be rotated by 180 degree, but 90 degree rotation is not allowed. Fischer projections that differ by 180 degree rotation are same. When a Fischer projection is rotated by 180 degree, vertical bonds still end up vertical and horizontal bonds still end up horizontal. Horizontal lines forward and vertical lines backward. Convention is maintained. Rotation by 180 degree is permissible. On the other hand, when a Fischer projection is rotated by 90 degree, we change the configuration of the molecule. The original projection has vertical groups backward and horizontal groups forward. When the projection is rotated by 90 degree, vertical bonds become horizontal and vice versa. The viewer sees a different molecule enantiomer of the original molecule. Thus, 90 degree rotation is not possible. It's also permissible to keep any one group fixed and rotate the other three groups clockwise or anti-clockwise. Now, coming to the conversion of flying wedge formula into Fischer projection formula. For this conversion, the group represented by broken wedge or broken line is kept at the bottom of the Fischer projection formula, and the remaining three groups are arranged in the same sequence, that is clockwise or anti-clockwise, as they appear in the flying wedge formula. The group which is placed at the bottom of the Fischer projection formula is kept below the plane of the paper and represented by broken wedge or broken line. The other three groups are placed in the same sequence as present in the Fischer projection formula. Next is conversion of Fischer projection into Sawhorse and Newman projection formula. The Fischer projection is directly translated to Sawhorse projection or Newman projection, considering that Fischer projection represents eclipsed conformation. The front or the rear carbon of the Sawhorse or Newman projection is rotated to get the staggered conformation. Now, coming to geometrical isomerism. In compounds where rotation about a bond joining two multivalent atoms is restricted, then suitable substitution leads to geometrical isomerism. Restricted rotation of groups and hence geometrical isomerism is possible around multiple bonds, carbon-carbon, carbon-nitrogen, nitrogen-nitrogen double bonds, and around rings. Geometrical isomers, also called as cis and trans isomers, differ in the geometry of groups on the double bond or ring. Isomers with similar groups on the same side of the double bond are known as cis, and those with similar groups on opposite side are known as trans. Geometrical isomers are distereoisomers. The necessary and sufficient condition for cis-trans isomers to exist in alkenes is that one substituent at each end of the double bond must be different from the another. For example, one butene has two identical hydrogens on one end of the double bond. Reversing their position does not give a different compound. The molecules which do not show geometrical isomerism are propene, but1-ene, isobutene, and cyclohexane methylene. For an alkene to show geometrical isomerism, the groups on same side of the double bond must be different. Now, coming to nomenclature of geometrical isomers. There are two ways to name geometrical isomers in alkenes, cis and trans nomenclature. In case of molecules where at least one group attached to the left carbon is equal to one attached to right carbon, the geometrical isomers are named by prefixes cis and trans. Isomer having two similar groups on the same side is called cis, and the one having two similar groups on the opposite side is called trans. Cis-trans nomenclature system is simple to apply. The terms are mostly appropriate for use with disubstituted alkenes, but this method of nomenclature cannot be used when all the four groups are different, and for such isomers we use E and Z system of nomenclature. Now coming to E and Z system of nomenclature. This method of nomenclature of geometrical isomers is applicable to all cases and is based on Kahn-Ingold-Prelog system. The two groups attached to each carbon of the double bond are ranked in order of priority. If the two high-ranking groups are located on the same side of the double bond, the alkene is designated as Z isomer, meaning together. The isomer having two groups of higher priority on the opposite side of the double bond is designated as E, meaning opposite. In most of the cases, Z is equivalent to cis and E to trans, but this may not always be the case. The relative priorities of the two groups bonded to sp2 carbon is determined by following rules. First, if two atoms with different atomic numbers are attached directly to the double bond, the atom with higher atomic number has greater priority. Thus, if oxygen, hydrogen, chlorine, bromine, iodine and nitrogen are compared, the precedence decreases in order: iodine greater than bromine, greater than chlorine, greater than oxygen, greater than nitrogen, and so on. Second is, isotopes of same element having higher atomic mass have higher priority. Third, when two atoms attached to the sp2 carbon are same, compare the second atom in the chain and continue until a point of difference is found. For example, CH2CH3 takes precedence over CH3 as carbon of methyl group is bonded to 3 hydrogen atoms, while carbon of ethyl is bonded to carbon and 2 hydrogen atoms. Thus, ethyl has higher priority than methyl as carbon is greater than hydrogen. Fourth, in case of groups having double bond, the priority system treats as if it were singly bonded to 2 of those atoms. In case of groups having triple bond, the priority system treats as if it were singly bonded to 3 of those atoms. The EZ nomenclature system can be used to any alkene that is capable of exhibiting cis-trans isomerism, including disubstituted alkenes, for which cis-trans nomenclature can also be used. The EZ or cis-trans isomerism can also be applied to systems with more than one double bond simply by including the atomic number in front of each descriptor to specify which double bond the descriptor refers to. For an alkene with one carbon-carbon double bond that can show cis-trans isomerism, 2 cis-trans isomers exist. For an alkene with n number of carbon-carbon double bonds, each of which can show cis-trans isomerism, 2 raised to power n number of isomers can exist. Now, coming to cis-trans isomerism about single bonds or conformational distereoisomers. In butadiene and other molecules of the type A double bond CH, single bond CH, double bond B, there are 2 conformations, both of which are planar and differ in orientation of alkylidene group around carbon-carbon bond. The fully eclipsed conformation with a dihedral angle of 0 degree is called S-cis conformation, and the conformation with dihedral angle 180 degree is called S-trans. The slightly modified stereochemical descriptors S-cis and S-trans denote that the stereochemistry is about the single bond possessing some double bond character, which provides torsional barrier to the interconversion and slows rotation. The S-cis and S-trans conformations have important effects on the reactivity of system. In Diels-Alder reaction, the diene reacts in S-cis conformation. Some conjugated dienes and enones are fixed in either S-cis or S-trans conformation. Suitably substituted amides and thioamides also show cis-trans isomerism, as resonance gives some double bond character to the single bond and slows rotation. The isomers are classified by cis-trans or EZ nomenclature. Now, coming to geometrical isomerism of ring compounds. Presence of a ring, like a double bond, is restricted of free rotation. A cycloalkane has two distinct phases. Cis and trans isomers are possible if two different carbons on a ring are substituted by two different groups. If the two substituents point towards the same phase, they are cis, and the substituents facing opposite phase are called trans. This applies to rings of any size and not just cyclopropanes. For cycloalkanes having 3 or more highly substituted substituents, the cis-trans nomenclature is ambiguous. The RS system is used to define the stereochemistry of such compounds at each stereogenic center. The EZ system of nomenclature should not be used to assign stereochemistry of cyclic compounds. However, when a third substituent is different and at different position, cis-trans nomenclature is still used, but the notation is slightly changed. For such compounds with more than 2 differently substituted atoms, the configuration of each group is given with respect to reference group R, and the other 2 are assigned as cis C or trans T to the reference. The reference group chosen is the one on the carbon atom of lowest locant. Now, lastly, coming to the geometrical isomerism in nitrogen compounds, that is oximes and azocompounds. Oximes, that is aldoximes and ketoximes, and azocompounds show geometrical isomerism due to restricted rotations about carbon-nitrogen and nitrogen-nitrogen double bond respectively. Like alkenes, the double bonded atoms carbon and nitrogen are sp2 hybridized. The lone pair of electrons on nitrogen is present in sp2 orbital, which fixes the position of substituents around carbon-nitrogen, nitrogen-nitrogen double bonds, resulting in geometrical isomerism. Previously, syn and anti prefixes were used instead of cis and trans to designate these isomers. In aldoximes, when hydrogen and hydroxyl group is on the same side, the isomer is called syn, and when on the opposite side, the isomer is anti-isomer. In ketoximes, the prefix syn and anti indicate which group of ketoxime is syn or anti to the hydroxyl group. The isomers are now satisfactorily designated by E and Z nomenclature. With this, we come to the end of today's lecture. Thanks for watching.